is that remind you of molality. A 1 molal solution of sodium chloride has twice as many particles floating around in the water as a 1.0 molal solution of glucose. Glucose is a polar covalent molecule. It's a simple sugar. So it can dissolve in water. However, it does not break apart. And as you can see in the top part of my slide, an electrolyte, an ionic compound dissolved in water, breaks apart into its ions. Again, I'm using molality as my unit of concentration for this example because at extreme temperatures, molarity has drawbacks. Molarity is moles per liter, but volume can change if something's really hot or something's really cold. Molality is moles per kilogram of solvent. That wouldn't change. So again, first slide, it depends on what we dissolve in water, I guess is what this breaks down to. Ionic compounds versus polar covalent compounds will be different. And the key here is my example of salt dissolved in water of equal concentration of, say, glucose, a polar covalent thing, has twice as many particles in it. So on the whiteboard, when I drew out an example of dissolving a salt, if I drew out an example of dissolving a glucose, it would just be 1 glucose surrounded by the water instead. But if it's 1 salt, there's actually 2 particles here. And that plays a role in really my last slide of content. Something that's referred to as the Van 't Hoff factor. Again, a term that you're not going to actually have to know. But if we're trying to figure out how high can we elevate the boiling point or how low can we depress the freezing point, it's based upon how many particles are in the solution. Now this I don't know if that's that important. Here's an example. If I were to dissolve salt in water, there would be 2 particles for every 1 NaCl. 1 Na plus, 1 Cl minus. If I were to dissolve calcium chloride in water, there'd be 3 particles, 1 calcium, 2 chloride ions. The Van 't Hoff factor is trying to help determine how many particles are dissolved in water. The more particles that you dissolve in water, the more attraction that you have to overcome. And there's 2 ways that we can measure the amount of particles. We can base this off of molarity or molality or whatever unit of concentration you want. So for example, a 2 molar salt solution should be able to have more particles than a 1 molar salt solution. Okay, hopefully that makes sense. If you have a higher molarity of solute, it's going to disturb the solution more. Not only do we have to look at the molarity, but we have to look at the formula of the compounds as well. Because in calcium chloride, there are 3 particles when that gets dissolved. That's going to disturb the water more. That's going to have more ions floating around. So in other words, if I had a 1 molar solution of NaCl and a 1 molar solution of CaCl2, the 1 molar solution of CaCl2 would have a higher boiling point because there's more ions that we have to overcome their attraction. It would have a lower freezing point. It would have a lower vapor pressure. How about KNO3? What would the I value be for that? 2. It's going to break into K plus and NO3 minus. Remember, the NO3 is covalently bonded together. So we have to keep track of polyatomic ions don't break apart. The formula unit is there's 1 NaCl. So there's 2 particles, 1 NaCl. Yeah. Now, the reason why this is labeled little I is Alex noticed the equation for osmotic pressure. If you did that reading, there's equations for boiling point elevation, there's an equation. Freezing point depression, vapor pressure lowering has mole fraction in its equation. In our textbook, it first goes over to colligative properties, and then it does this section where it adjusts all of those equations to include the I value as well. So this I value, you're not going to have to know mathematically. It's just a way to label it so I don't have to call it the Van Hoff factor every single time. How many particles would sodium sulfate break into? 3. 2 Na pluses and 1 SO4 minus 2. And again, the key I have on the bottom here is the more particles that you dissolve in water, the greater the change to the freezing point or the boiling point. That's kind of the key here. There's 2 ways that we can identify that. Either based upon the molarity or molality. So what big number is the number for the concentration? Or we can identify based upon the formula of the compound. Ionic things break apart into multiple ions. The more ions you have floating around in the water, the more attraction that has to be overcome. So if you're heating it to a boil, you're going to have to heat it higher than normal because now you have to break all sorts of intermolecular forces. My very last slide is just an example of this. So if I gave you the same molarity, would a sodium chloride solution or a barium chloride solution have a higher boiling point? What's the formula for sodium chloride? NaCl. What's the formula for barium chloride? BaCl2, which means for NaCl, there's 2 particles floating around for every 1 NaCl. For barium chloride, there's 3 particles. So if they're the exact same molarity, the barium chloride solution would have a higher boiling point. It's kind of weird that the same thing that can make the boiling point higher makes the freezing point lower. But you're just taking water and you're messing with it. And when you're messing with it, you're allowing it to deviate more from its normal situation. One more. Sugar or magnesium fluoride? Probably don't even need the formula for this. Because sugar is polar covalent. It's not going to break apart into tiny little ions, unlike magnesium fluoride. Magnesium fluoride is MgF2, so there's 3 particles there. Sugar, there's only 1 particle. So the magnesium fluoride should change that. Last thing to note, which you probably don't have to worry about, but our textbook mentions, at some point, not only if you have too high of a concentration are you maybe not able to dissolve anymore, the solution becomes saturated so you can't add any more to change the boiling point or the freezing point. But at some point when you make too high of a concentration, sometimes these ions floating around will pair up. So it gives you a different I value than what you would have expected. Now this point I have here probably pertains more to the old AP Chem curriculum when we had to do the math associated with it, because then they'd give you sources of error. Because on any of those free response, when they give you a procedure, sources of error are very a common question. But it's kind of worth bringing up for your general knowledge that you can only increase the concentration so much of a solution to have an effect, let's say water as the solvent. At some point, it doesn't matter because it's either a saturated solution or all of a sudden these NAs are such abundance in the CLs are that they start attracting to one another. And then you actually have a dissolved NaCl, which is kind of unusual, but it does occur. The key here is knowing your colligative properties, which again, if you know the title of boiling point elevation, if I have water and I add salt to it, it's going to be a higher boiling point. Freezing point depression, if I have water, I add salt to it, I'm going to lower the freezing point. Vapor pressure lowering, if I have water, I add salt to it, it's harder for the gas to come out of that, so it's a lower vapor pressure. Knowing how osmosis works. The idea of water is going to flow from high concentration of water to low to get equilibrium if possible. I know our online textbook link has a good video that deals with osmosis. I try to do the example of the egg lab from the bio as well on your reading guide.
So the textbook doesn't just talk about water with osmosis? Can it just be, could it be any solvent?
It could be any solvent. I mean, water is most common, but it could be any solvent. I mean, just like the example I gave water here, it could be a non-polar solvent just the same, although your Van Hoff factor would be different. What I would say that you need to know is a little bit of the explanation, especially with boiling point and vapor pressure. I would say you don't need to know the explanation behind freezing point depression because that gets into disorder. Second thing, I like this stuff as a multiple choice style question where I just give you 4 solutions and I ask you which one is going to have the highest boiling point, the lowest melt, the lowest freezing point, lowest vapor pressure. And that's based upon that Van Hoff factor idea on this slide right here. Now, the practice problems you picked up on the way in is kind of a little practice in doing that type of skill. But like I said, 9 o'clock was when we wanted to be done, and now it's kind of dealer's choice at this point. You have a practice sheet you could work on. You have WebAssign that has some of this, and a little bit of review stuff that you can work on, and then you have the review guide as well. But that's what we got the rest of the day.